Okay, sample problem 11.2. Here we have a problem where we're going to be throwing up a ball and we're going to be at a location above the ground. Okay, so it says here you're going to throw up a ball vertically with a velocity of 10 meters per second from the window located here 20 meters above the ground. Knowing that the acceleration on the ball is going to be due to gravity, 9.81 meters per second squared downward, they want us to first determine the velocity of v and the elevation y of the ball above the ground at any time. So that's really just figuring out, what those values are per the unit of time. Now, because we're starting with acceleration this time and not the position, we're going to actually be doing integrals up to get the velocity and then the position equations. Okay. They also then want us to determine what is the highest elevation reached by the ball and the corresponding value of the time for that. And then the time when the ball hits the ground and the corresponding velocity. And then it says draw the motion curves as we see it here. So our Excel spreadsheets kind of have us set up really nicely, but we need to do a little bit of math so that we can fill in our equations for each one of the motion curves. Now, for this one, because we're given acceleration, as I said earlier, this time we're going to do integrals to get the velocity and the position equations to fill in for the motion curves. So let's go ahead and I'm going to start by kind of getting this is sample problem 11.2. Okay. And what we're given here, all right, we're given that our original velocity. Now, a lot of times, probably in physics or previous classes, we would use the letter lowercase I for like initial velocity, F for final velocity. I'm not sure why, but this book always uses 0. So I refer to it as original or origin 0, I think is what they're trying to say. So this is like an initial velocity. I'm going to keep it the 0 like they use only because then it corresponds with what the book has. Okay. So our original velocity that we start out as is going to be 10 meters per second, and that's going to be going up. Okay. Now, up is going to be the positive convention for this problem. Okay. So since that's the case, our acceleration due to gravity is going to be a negative 9.81 meters per second squared because it's directed down. Okay. So that's going to be given. Now I like just showing a little diagram so that we kind of know where we're at. This is going to be our 0 meters down here. So this is going to be like our origin. Okay. Positive would go to the right. We're only going to be dealing in verticals. Positive is going to be going up. And then our ball is going to be right about here. And its initial position is going to be that 10, or its initial position is going to be 20 meters above the ground. Okay. And it's going to be thrown up at a velocity of 10 meters per second. Okay. Now, first things first, like I said, we need to determine our equations for each one of our curves so we can fill them in Excel. Okay. So because we're starting with our acceleration, then we're going to do the integral to get to the velocity, and then again to get to our position. So step number 1 is going to be using our acceleration. We're going to integrate to find the velocity curve equation. Okay. So we know that dv over dt is equal to acceleration. All right. And we know that's equal to a negative 9.81 meters per second squared. Okay. Now, we want to solve so that we get the velocity by itself because we want to find the velocity equation. So we're going to say dv is going to be equal to our negative 9.81, just substituting that for the acceleration, times dt. You don't need to hold the units through these equations because they're not going to end up canceling out. Okay. All right. Now we're going to take the integral of each one of those sides. So we're going to take the integral of dv, and our limits are going to be the velocity at any given, time from our original velocity. So our original velocity is going to go down at the bottom, and then the v is going to go at the top. It's going to be equal to, we're going to pull that negative out front of the integral, and this is going to be the integral of the time. So we're going to go from a time 0 at the bottom to whatever time we're interested in, so to t. And that's going to be 9.81 times dt. Right. So then doing the integrals there, we're going to have well, I always do an intermediate step. You don't have to if you don't want to, but this is how I learned and how I always did it. So I'm just going to pull out my v. I'm going to put my limits from v, and our original velocity was 10. So I'm just substituting that value of 10 at the bottom because that's, if you would, a constant. That's where we're starting. And then it's going to be equal to that negative 9.81 and then t is at the top and 0 is at the bottom here. Okay. So now doing the integral, we're going to get v minus 10 is equal to negative 9.81 t. Okay. And then it would be minus 0, but we don't have to put that. Okay. Now, solving for v, because we want our equation to be v is equal to, we're just going to take that negative 10 and put it on the other side. So v is equal to, this is going to be 10 minus 9.81 t. And that's it, right? Because the negative 10 becomes positive on the other side. And this is our equation for our velocity curve. Okay. Now we're going to take the integral of the velocity curve to get the position. Okay, so if you recall on my little equation sheet, we're going in this direction up. We started with acceleration, we integrated to get our velocity. Now we're going to integrate a second time to get the position at the top. Okay, so now we're going to take, is that right? So our velocity is equal to dy over dt, which we know this is our velocity on this side. This is going to be our 10 minus 9.81 t. Okay, now solving for dy, we're going to multiply this then times the dt on the other side. So we're going to do the dy is equal to, and I'm going to put the 10 minus 9.81 t times dt over here. Okay, I'm going to add my integral to the front of each one of these, and then I'm going to put my limits. So I'm going to start at the bottom here. This is going to be my distance. So I'm going to start at my original distance, my YO, or my initial distance. And that's going to be equal to my 20. So this is equal to Y original. Okay, that's where we're starting. And then any value of Y. And then for time, I'm going to start at time 0, and I'm going to go to any value of time that I want to know, right? So that's going to be the 0 on the bottom and the t up on top. Then again, I'm going to do that little intermittent step. You can do it or not. It's up to you. I know that my y here is going to be any value of y, and my y0, or my original y, is going to be the 20. Okay? Because again, that's equal to where I'm starting when I throw that ball up. And that's going to be equal to 10 minus 9.81 t. And those limits are going to be 0 and t. And then, so doing my integral, I'm going to get y minus 20 is equal to 10t minus, now I have to divide that in half because of the power. It's going to be 4.905. So minus 4.905 t squared. Now solving for y, I'm going to take that 20 and put it on the other side. So I'm going to get y is equal to, now I'm going to put my square first. So I'm going to kind of put it in the order of what would be the quadratic form. So I'm going to do a negative 4.905 t squared plus 10t plus 20. Does that make sense? Okay. And then this is the equation for the line on my position curve. Okay. So again, integrating twice. So now that we have our three curves, we can go over to Excel and we can populate the cells for that. So pulling up our Excel for our meters, okay, I am going to start on my position graph, okay? And I'm now going to populate my column X with the equation. So that last equation that I have is the negative 4.905 times the time squared. So I'm going to say equal to negative 4.905 times, now here's my time, and that's going to be squared, plus 10 times the time plus 20. So I'm just double checking negative. That should be good. So I end up with 20. Okay. And then I'm going to take that value and I'm going to copy it all the way down. Okay. There we go. Guys get the same values? Look the same? Okay. Too many pieces of paper here. Hold on. So look, here it is. Yeah. So if you want to compare with the book, you can simply go to page 625, and this is going to be your position time curve. And if we go here, it's starting at 20, and we start at 20 as well. Okay, just as a confirmation, it's just kind of nice when you have those sample problems, just to be sure, put everything in correctly. Now we're going to go to our velocity, okay, and do that very same thing. So now we're going to use our velocity equation, which was equal to 10 times the time, nope, 10 minus, sorry, 10 minus 9.81 times the time. Okay, so that's going to be 10, which is correct. I'm going to reselect and I'm going to copy all the way down. And that's a straight line. That looks good. Okay. And then my third curve, which is going to be acceleration. Okay. Now acceleration, I'm going to get rid of these guys from the previous problem I did. I know that this is a negative 9.81 for all of them. So there isn't an equation here. It's just a value. It's constant acceleration. I'm just going to copy that down. And then the curve is just a straight line along that negative 9.81. Okay. Now, you want to go ahead and you want to save this as sample problem. Let's see. Sample problem 11.2. Okay. So we've got our three curves then for each one of these. All right. And now we want to answer the questions. Okay. So let's take a peek underneath and look at our questions. And it said for our first one, the velocity v and the elevation y of the ball above the ground at any time. Okay, so we did that through the Excel spreadsheet. So for part A, that Excel spreadsheet, the curves, okay, for the position and for the velocity, we can put any time in here and we can figure out what the position or velocity would be. So that takes care of part A. So I'm going to go back underneath here and I'm going to go to my second page here. So question A, see Excel spreadsheet curves. Okay, so you'll just take a screen snip of each one of those and you're done. Okay, does that make sense for everybody? Okay. Part B. Okay. Part B, it says, what is the highest elevation reached by the ball and the corresponding value of time? So what is the time when we are at its highest point? Okay, what is the time at its highest point? So we throw it up at 10 meters per second. It's going to go up for a little bit. What is the highest point that it's up? Okay. So if we look at that, I'm just going to kind of go back over here. So that means we're going to, if you would, go up and it's going to get to a high point right here and then it's going to come down. So we want to know what is the time to get to there? And also, what is that highest value? What is that value? So what is something about that point that we know? The velocity would be zero, right? Because that's going to be the point at which it stops moving, it changes direction, it's going to start coming down. So that's going to be the very highest point. So we want to know what is the time when the velocity is zero. So let's look at that velocity equation, okay? Our velocity equation doesn't have a square in it this time, all right? So what that means is we can set this velocity equal to zero and solve for what t is, right? So we're going to do that. We can do that directly. We don't need the Excel little calculator to help us with that. So we're going to take this equation. So for part B, we're going to say v is equal to 10 minus 9.81 times t. Okay. And we're going to set that equal to zero. Zero is equal to 10 minus 9.81 t. We're going to solve for t by moving 10 to the other side, negative 10, negative 9.81 t. These both become positive, and then we divide both sides by 9.81, and our t should come out to be 1.019 seconds. Right. Now, that is part of our answer because it wanted to know what is the time at its highest elevation, right? Okay. But now it also wants to know how high is it? How high is it? Okay. So if the time is 1.019, okay, we could go ahead and use that time and put it into this equation here for our elevation, right? We could manually do that. Or we can use Excel. So let's go over. We already programmed that equation in, right? So if we go back to Excel, we're on our position tab, okay? I'm going to add a time of 1.019, oopsie, sorry, 1.019 seconds right here in the time column, okay? And then I'm going to take you can take any one of these. I'm going to take the top one and I'm going to right click and I'm going to copy that cell, okay? And I'm going to paste it right next to my 1.019 paste. Now, it's going to use and double check. You want to make sure that it's using the time in cell A12, and it is, okay? By copying it down, it increments, those values. So my value comes out to be 25.096, blah, 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 blah. All right. So I'm going to, oopsie. I go back over here. I'm just going to highlight that because you could do a screenshot here if you wanted to. All right. Or you can go over here and just say y is equal to 25 point, what's the number? 25.0, try 25.1, 25.1, because it's 0.968. And that's going to be meters. Okay. And you can say from Excel. Okay. But again, you could manually calculate that if you would like to. Okay. Totally up to you. But since we had it already calculated and programmed, it was easy to do. So let's look at part C. Part C. Here it says the time when the ball hits the ground and the corresponding velocity. Okay. So if we look back at our little diagram here, so now it goes up, right? We found out how high that is, 25.1 meters. And now we want to know, okay, what is the time when it hits the ground? And what is the velocity right before it hits that ground, right? Okay. So what do we know about this? This is going to be a time when what is zero? Go ahead, Tyler.
Position.
The position is zero. Exactly. So if we look back at the equation for position, right? Here's our equation for position. It's got a couple squares in there for t, right? So if we set this equal to zero, we can't solve for t directly, right? Easily manually. So we need to use that quadratic equation, which we already have a little calculator for. We can go back to Excel here, go to our time tab for this problem, and now we can use our quadratic formula here. So our position equation is y is equal to negative 4.905 t squared plus 10t, whoopsie, plus 20. Okay. Now make sure you change your 2 to a superscript. Okay. Now, you don't have to put the velocity and the acceleration equation in if you don't want to, because we're really not using those. We're just using the position equation. So now we just want to put in the variables for the A, B, and the C. So our variable for A is going to be negative 4.905. Our variable for B is going to be 10, and our variable for C is going to be 20. You should get negative 1.24 as one of them and 3.28 as the other. The 3.28 is going to be the time when the ball hits the ground. Oopsie. Okay. And then you can also add over here. So T equals 3.28 seconds. All right, that's an answer when ball hits ground. Okay. And then we need to know what the velocity is at that time. Okay. So here again, we could turn this over. We could use our velocity equation, put that time in here, manually calculate it, right? Or I'm going to use Excel because I've got it programmed already. So I'm going to go back over to my Excel spreadsheet. I'm going to go to my velocity tab. And right down here, I'm going to put that time of 3.28 in my time column. And then for my cell here, I'm going to copy one of the values along that column for velocity. I'm going to say copy. And I'm simply going to go down right next to my time, and I'm going to paste that in position. Oopsie. There we go. And I get a negative 22.2 meters per second. And I'm just going to highlight that. All right. You guys get that same number? And now I'm going to go back over here, and I'm going to say my velocity is equal to a negative 22.2 meters per second. And that's when the ball hits the ground. Now, negative 22.2. Does that make sense? Does the negative make sense? Yeah, because if I look back at my trajectory here, it goes up, right? So all of these, until I get to the top here, the direction of the velocity is going up. But as soon as I switch directions and I start going down, now my velocity is going down, right? So it's going down in a negative direction. We identified up as positive, so that's why we're seeing it as coming out as a negative value. So it does make sense. Okay. All right. Now to hand in for this one, basically any of the work that we did here, okay? And if I turn over, it's going to be those guys. And then any screen snips, that show that you did the calculations. So for instance, the quadratic form, you would do a screen snip here. If you use this as your calculator for the position at that time 1.019, then you want to do a screen snip here. Same thing for the velocity, but either one of those you could also manually calculate by just plugging in those values for the time. Does that make sense to everybody? Okay, so I'll let you choose how you want to, do that. So that is sample problem 11.2. Okay, so if we look at the homework that you have assigned, okay, let's go to Canvas, right? Actually, I'm going to stop the recording here.